Hello and welcome to today's session, Operating a Multi-Petabyte System of Record for Billions of Users. My name is Matt Bichelle, Senior Director of Product and Solutions Marketing at Aerospike. I'm pleased to be joined today by two presenters from Verizon Media, Olli Virtanen and Joe Francis. I wanted to say that about a year and a half ago, it was announced that Aerospike would power Verizon Media's global data platform. And overall, Verizon Media has undertaken this modernization effort for a system that Olli and Joe will take us through. Joe heads up the team that provides key value storage and messaging systems for all of Verizon Media, and Olli is the architect. So without further ado, I'll hand it over to Joe.
Thank you, Matt. Good morning, everyone. In this session, we are going to cover, an introduction to Sherpa and, about how we moved all the data in Sherpa to Aerospike from its current existing backend. What exactly is Sherpa? It's a key-value store. It's a large-scale system distributed across the world. It supports a schema-less system. Data is replicated across multiple installations in data centers that are present across the world. And the model is eventually consistent. There's no global transactions or transactions across records. It has been in production since 2008. And it has gone through multiple, incarnations, during its lifetime. It is primarily hosted as a web service meant for consumption by organizations within Verizon Media, which was previously Yahoo. And from the perspective of those users, it's a hosted key-value system which is elastic and highly available. A little bit about the scale of Sherpa. We operate in majorly three regions across the world: Europe, APAC, and Americas. We have multiple data centers in those regions. We have around 200 billion or more records, in total a petabyte of data. We serve up to 5 million read requests per second, mostly for serving use cases, and hundreds of thousands of writes per second. I mentioned that Sherpa was launched in 2008. Originally, it was launched using MySQL as storage. And as hardware evolved and tech evolved, Sherpa also evolved. We moved to a LSM-based storage engine in 2013. LevelDB was the backend store at that time. It was suited for handling writes in a much better performance. And then after RocksDB came out, we actually transitioned that to RocksDB. And today, we are talking about the next stage in that evolution, which is basically, storage has changed, and hardware has also evolved, across, the last few years. We now have persistent memory and, much cheaper flash drives. So that's what the driving factor for our, transition. So when we go through these hardware cycles, we take a look at, the total stack, including hardware, software, everything. And we look at it with a very open mind, right from starting with, should we even run this? Should we even do this? Right. And the result of this analysis is what made us move to Aerospike. But our core, goals with this kind of evaluations is like, how can we provide a much better user experience at lower cost? And with that in mind, we tested out many key value stores. We haven't listed everything in this graph, but it kind of represents the things we found out during that exercise. And Aerospike was the best fit in terms of performance and closest to our features. And the numbers that we show here are representative of what Sherpa does with these backends. They're not really a test of what the system does on its own. So we tested Sherpa on these systems, and we found out that Aerospike would suit us the best. I said the best, but it was not the perfect fit. There were some gaps that needed to be addressed. And I'm just mentioning the important ones here. One was the eventual consistency model we have, which is very different from other systems out there that have a very different policies, like the last update bins, or something else, distributed transactions. So for this, Aerospike did have to implement some changes. The bin level convergence feature was something they released based on our requirements, and we also supply change notifications to our users, and we basically use Pulsar as the standard messaging bus in our company. So we wanted support for Pulsar for notifications. So those were the two big items that Aerospike had to provide. A lot of the other features we built on top of Aerospike, including all the concepts that evolve around multi-tenancy, like security, isolation, and quotas, throttling, rate limiting, all of those things. Plus, we have in Sherpa, globally ordered tables, tables that can be scanned based on an indexed key. So that is something which we have built on top of Aerospike within the application layer. With that, I will hand over to Olli, who is the architect for these systems, to do a deeper dive into some of the implementation details.
Thanks, Joe. So I'm Olli Virtanen, and I'll be going through some of the details of what we use Aerospike for in Sherpa. We'll start with this architecture diagram, where we start with our customers who are internal only. Our customers can use either Sherpa's shared client library, or they can roll their own client if they so wish. Whatever they do, they first contact the DNS, of course, to pick the data center which will be handling their traffic. And within the data center, all their traffic goes through a fairly normal load balancer. The traffic then goes to Sherpa's application logic, which is in the API layer. Those are fairly lightweight Java-based applications based on a undertow HTTP serving stack. The API then contacts the Aerospike nodes, which are fairly beefy ones with loads of persistent memory and fairly large NVMe devices. Altogether, we have some 400 to 500 of those. Now, within Aerospike, we then have our custom multi-tenant data model, which is replicated across to other data centers using Aerospike XDR only, because we want to use that one to avoid duplicating any traffic. Internally, we'll also then use the Pulsar Connector for certain change notifications. And watching over everything, we have Yamas, our monitoring system. Now, every bit of traffic in this diagram and in our architecture is also protected with mutual TLS, which means that every connection has a certificate on both ends, and both ends validate the other one. So our multi-tenant capabilities, we think that Sherpa should be as much as a public cloud service as possible, which means that our customers can create tables as they wish. They go to a friendly portal application and submit their requests. And then we do some sanity checking and establish table metadata, which is naturally stored in Aerospike. Now, parts of that table metadata come from the user directly, such as access policies and request rate provisioning data. The system then picks a namespace and set in Aerospike where the data will be stored. Since the Sherpa data model is schema-less, we need to store the field names in addition to the field values on every record because of Aerospike's bin name limit. We also use multiple namespaces for flexibility in capacity allocation. We have some half a dozen namespaces, which we expect to grow fairly equally, but some will grow faster than the other. So we will be allocating disk partitions to those namespaces as needed. The 1023 set limit per namespace in Aerospike is also a reason why we use multiple namespaces. So then to protect customers from each other and in some cases from themselves, we also have a rate limiter within the Sherpa API, and that is implemented using a custom UDP-based distributed approximating counter service. So data replication, we have those 6 data centers where this Aerospike Sherpa is running. Within each data center, every record is stored in 2 copies. We use the Aerospike strong consistency mode because for us, the partition availability loss is going to be a smaller problem than the recovery from a split brain in AP mode. Customers can choose which data centers they want to be present in, but every table is in at least 2 locations, and we know that some locations are not okay for all kinds of data due to legal compliance. From history, we also know that some locations are going to be significantly less used than others, so we've already allocated less hardware in those places. In Aerospike, this geographic selection is configured with set level filtering in the XDR configuration. And then on the XDR part, we also use the bin convergence to allow our customers to write concurrently in multiple data centers into the same fields of records. So in this case, when somebody writes to one record's field X in multiple places at the same time, we accept that one of those writes will be overwritten, but it's as long as all of the data centers then eventually converge on a single value. And we expose some of that XDR propagation to our customers through a construct that is very much like a version vector. So when these concurrent writes occur, each data center will initially have a different version vector, and then when all the XDR dust settles, they can observe that the version vector has become the same everywhere. For change notifications, we use Apache Pulsar, which is an open source pub subsystem initially implemented in Verizon Media. It is now a top-level project in Apache. Out of the alternatives out there, we think it is the best on performance and easiest to scale to very high message volumes. In Sherpa, we use the Aerospike Pulsar Connector and XDR forwarding to maintain ordered indexes because change notifications from XDR are pretty much the only way to get a glimpse into XDR updates without explicitly reading records. Sherpa has also change notifications that are delivered to our customers, and these have to be implemented in the API layer because those report changes to records with old and new values, and XDR isn't just a transaction log like that. Additionally, the change notifications for customers have custom field lists and have to be compatible with the original Sherpa message formats. So for all monitoring, we use Yamas, which is Verizon Media's monitoring solution. Our take is that it scales better than any of the available monitoring services out there. In fact, we use a single Yamas to monitor all of the servers in Verizon Media, and those produce billions of time series all the time. Now, the next version of Yamas will also start using Aerospike to store its metrics data. And the Yamas team is also in the process of open sourcing the whole thing. So in Sherpa, we monitor Aerospike directly using a custom collector plugin, where we're also increasingly moving to Telegraph-compatible collectors. The API layer, on the other hand, reports to Yamas directly using UltraBlue metrics. Now, all the hosts are, of course, also reporting low-level data to YAMLs in the background. Now, the graph here is a snapshot of read and write query performance in Sherpa over a few days as rendered by YAML itself. So for security, we try to use all kinds of security measures in Sherpa to protect our customers' data and overall. Some of the cornerstones are Athens and CKMS. Athens is another open source project that was started at Verizon Media. It is now a CNCF sandbox project. And at its core, it's a platform for certificate-based service authentication and authorization. It replaces credentials-based authentication with certificates. It also provides fine-grained authorization logic. In Sherpa, our goal is to replace credentials-based authentication against Aerospike with certificates entirely. Now, all customer requests are already fully validated with Athens in Sherpa. CKMS then is a centralized key management system. It is internal to Verizon Media for the foreseeable future. It ensures key access controls and rotation policies so that we don't end up with 5-year-old secrets somewhere. We are hoping to make KMIP support into it fairly soon. In Sherpa, we use it primarily to store disk encryption keys. On the operational side, our CI/CD platform is Screwdriver. Once again, Screwdriver is an open source project developed at Verizon Media, and it is incubating in the CD Foundation. Screwdriver drives all of Sherpa's deployments and OS upgrades, both on the API layer and for Aerospike. At our scale, there are no maintenance windows, so these deployments run against the live system in the larger scope, which means that whenever some nodes are down, that's fine as long as the whole system is fully functional. So to the Sherpa customer, there is no visible downtime. We deploy Aerospike configuration changes multiple times every week to roll out customer change requests. Now, some of those configuration change pipelines are rather involved, so we are always on the lookout for more dynamic alternatives. So the migration to the Aerospike-based Sherpa is a big process. All of that data has to be moved. It is not complete yet, and we have mentioned before that this isn't the first time Sherpa is being migrated either. So we are fairly confident that with the key enabler of Sherpa's stable API, this is going to be a success. One of the primary promises that we have made our customers is that they don't have to make any changes to their applications because of this migration. And while the migration is in progress, the new Sherpa will be proxying traffic from the old to the old system wherever that data hasn't been migrated yet. We also use the proxying capabilities to track performance and consistency between versions with pass-through writes and shadow reads that have been used to ensure that our scalability is correct. Naturally, all that proxying code will be torn away once the migration is complete, since we don't want to maintain dead code. We're currently about halfway done and expect to finish sometime in Q3. On the horizon, the one thing that we are actively waiting for and will be activating in Sherpa as soon as possible is the set index stuff. One of the actions our customers can do against their tables is a full or partial table scan. And unfortunately, the amount of those scans came as a bit of a surprise, as the cost of those against Aerospike. Now, in hindsight, it of course should have been obvious that scanning 100K records for each one that is returned would take time and CPU, but that is one of the costs of packing multiple tables into a namespace. Regardless, we will be enabling the set indexes on table-by-table basis and expect all of our troubles on that aspect to go away. Thank you.
Okay, well, thank you, Olli and Joe, for a very detailed walkthrough of the Verizon Aerospike system. I'd like to take some time and ask you each or collectively some questions, if that's okay. And so with that, one of the questions that comes to mind, given the size of the data, I don't like to overclassify or put labels on it, but when you're talking about petabytes of data, the first thing that comes to mind is it might be hotter or colder data. I was wondering if you could each talk about kind of the nature of the data set and how it operates in that regards in terms of how frequently it's accessed and maybe what some of the SLAs are for your customers to the data.
So let me take a crack at this. So we host a multi-tenant system. So I cannot put all the data into one bucket. Okay, there's data. There are tables that get frequently updated. Then there are huge tables which have historical data versus current plus current data. There are small tables. There are large tables, and then there are tables where data expires. They have set expiry, which is a feature Sherpa supports within the application layer itself. You can have fields expire and rows expire. So all kinds of data, about 5 million RPS per second. That's reads and about 300 to 400,000 writes per second. So that gives you an idea of how frequently it gets updated and how much it's accessed. Do you have anything to add to that?
Yeah, and one of the things we kind of decided early when we were evaluating the different data stores was that our assumption is that there is so much data that is being accessed that there's not really a way to say that some part of it is cold or warm. So caching would not be a very beneficial thing for us. So that's why we were kind of happy with the constant performance across all of the data in Aerospike.
Something we like to try to take pride in for sure. Given that this is a migration, and I wasn't sure if you stated in the presentation, or maybe it's just plainly obvious, is the majority, are these all on-premises data centers, the 6 locations, or is there a mixture of cloud and on-prem?
So
as of today, they are. Yeah,
go ahead.
As of today, they are all on-prem in our own data centers running on bare metal, but that could change. I mean, it's not that, it's cast in stone. We are looking at, options to at least move some part of it to the cloud, some in clusters of it. But the migration itself is within our existing data centers.
Yeah, there's nothing really much to add to that. Yeah, well, as you said, Joe, there are different workloads, and so it's certainly not monolithic. So I can certainly see portions of it be evaluated. Is there any special hardware that you're considering or using, or is it does Verizon have its own hardware configuration that it prefers with Aerospike already?
So we did a series of, collaborative tests with Aerospike, solutions, before we decided to buy the hardware. So it is kind of custom built for Aerospike, even within the configurations we have. But it is standard for all Aerospike clusters, within the company. So if you ask about standardization, yeah, there is a predefined config for Aerospike within the company, but it's not used across a lot of other, storage use cases. So this has persistent memory and high performance in NVMe drives in this configuration.
a little bit related. I don't know, Olli, if you wanted to add anything to that.
Well, the persistent memory, maybe going to that a bit. So one of the early choices we made was to take the persistent memory into use, because with that we get into a significantly shorter kind of turnaround when we are upgrading the clusters, because one of the problems that we thought we would have was that if Aerospike needs to scan all of those terabytes of data per node whenever we reboot it, that would become a problem. So we were happy to find out that this persistent memory would cut that away almost completely.
Yeah, I mean, that's one of the, in a way, cold restarts. In a way, this is a sort of cold restart when you migrate. So that is one of the benefits of persistent memory. So I think that's maybe a slightly different angle of a benefit of PMEM and being able to get up quicker from a zero or a migration. In terms of other things that are, I guess, a little bit new that were alluded to in the presentation, you talked about kind of anticipating Aerospike's development of the Connect for Pulsar Connector, just in terms of its functionality, like at a high level, how well or how satisfied are you with its performance currently, and might there be things that you're looking for from the Connect for Pulsar connector?
I think I'll let Olli handle this.
Yeah, so we're using the Pulsar connector specifically to get a glimpse into the XDR updates for our ordered tables. And without having something like that, we would have had to, well, make completely different kind of design for that whole thing. And that might have been something else than Aerospike in that case. So for us, it's a kind of a critical component.
Well, it sounds mission critical for sure. Then, well, I'm glad that Aerospike has it then for all, not just for Verizon. You just mentioned it. I wanted to ask a little bit about your ordered indexes. Is this standard across all of the Aerospike workloads? What are some of the benefits of it?
No, so the ordered tables in Sherpa are, well, we have two different kinds of tables. There is an unordered table, which is we call a hash table, and then there is an ordered table, which also can be accessed in a kind of hash table-like a way. So you can always ask for a record from any table. But the ordered table then builds the top of that the kind of concept of key ordering. So we can have customers who have like a prefix of a record key and they want to scan forward from that. And that just would not be possible with a hash table. So there is probably a bit less of ordered tables than hash tables, but it's not a big difference in amount, really.
Might you say, would it offer some speed for some of those use cases, like the look forward into from a historical perspective?
So there is at least some use it to kind of extend the concept of how big records can be conveniently, or if they want to access records partially or things like that, they might build an ordered table. But then we also kind of piggyback an ordered secondary index on top of that is persistent and integrated with the workflows, that then becomes a more kind of classical secondary index access thing.
Okay. Yeah, certainly makes sense in that regards. Okay, I'm just looking at the time. I think I'll kind of conclude with this final question or comments or observation. So I thought, I heard you guys talk about eventual consistency between data centers, but you have strong consistency for replication within a cluster. So could you just comment a little bit about that? And are you looking, what are some of the benefits that you reap from the strong consistency within the cluster that you don't necessarily need across clusters?
Within the cluster, you expect read after write consistent. Most applications, go, bind to a certain data center at a given time. And if you look at our use cases, they are mostly localized, to certain specific locations for certain users. And so you would like to have, read after write, consistency within that, data center. But there are cases when, different applications update different columns in a row, and that's the case when you want those updates to get merged, right? So that is where eventual consistency comes in. That you don't see one of your updates disappear. Right. So normally most systems don't do this. They, if you have two conflicting updates across geographies, one of them is declared the winner and the other one is just wiped out. So here we have the feature where where you have two different updates happening in two different geographies, and when replication is done, you have both those updates present in both those geographies.
Oh, sounds like the best of both worlds.
Yeah.
Okay. Well, again, we're out of time for this session. Joe and Olli, if you're willing to take, for people to contact you within the platform, I think that'd be great. Again, thank you both. Really appreciate the time, and hopefully our audience did as well. So thank you again.
Thank you.
Thanks, Matt.